We will
This
be going.
conference will now be recorded.
So these are the few topics which we will be going to cover in depth in today's demo session. So okay, so if you have any doubt at any point of time, you can unmute yourself and you can ask me. I will stop there. I will explain that topic and then I will move further. Okay. So the first topic is what is signal integrity. So as you can, if you break the terminology signal and integrity, so signal is nothing but a electrical energy, a electrical form, you can say voltage or current, which carry data from one place of a circuit, from one point of a circuit to another point of a circuit. Let's say you have 2 points. Let's say point A is the driver which is driving that signal, and point B is the receiver. So signal is basically a electrical energy in form of voltage or current, okay, in form of, in digital it is 0 1 1 0, all that, which carries some data, which carry information from point A to point B. Okay, and integrity means the characteristics of a signal. So the signal integrity means, in signal integrity we study characteristics of a signal when it is traveling from point A to point B.
This conference will now
So
be
now
recorded.
the question now the question comes, so what is the need of doing the signal integrity analysis? What is the need, why we should do the signal integrity analysis? So let us understand with a very basic example. So let's say we have two conductors, or we have two wires which is going side by side of each other. Okay, it is in very close proximity of each other. In one conductor I'm transferring a signal of frequency 50 megahertz, okay, which is a high frequency signal. And in another conductor I am sending a signal which is low frequency, let us say 5 kilohertz. So now because of the high frequency signal, that 50 megahertz signal, so 50 megahertz signal means in 1 second, the signal is transmitting 50 into 10 to the power 6 times. So from 0 to 110, it is the frequency is 50 into 10 to the power 6. So it is it is rapidly, it is switching signal. So as we all know that from the Faraday law of electromagnetic induction, so a changing voltage, that is from 0 to 1, 1 to 0, 0 to 1, like that it induces, so voltage is changing over here, which induces a changing magnetic flux. Okay, so a magnetic flux will be produced around the conductor A, around the wire A, and since the wire B is near to wire A, there will be some of the flux will get induced into wire B also, which is carrying a low frequency signal of 5 kilohertz. Then because of this magnetic flux linking or magnetic flux coupling, again the law says if there is any changing magnetic flux around the conductor, then it induces a voltage across it. So because of the changing magnetic flux from A getting linked to B, there will be some amount of voltage inducing into B. Although, okay, there is no any electrical connection between A and, but there will be some voltage induced in conductor B because of the magnetic flux coming from conductor A. So because of that voltage induced, we will get some noise on the 5 kilohertz signal in the conductor B. Okay, and because of that noise, the conductor B signal will be noisy and it will lose its property, or it will lose its integrity. Okay, this is a basic example of what is signal integrity, and one of the very prone. So this is called as the crosstalk, okay, which we will be talking about more depth in the further slides. This issue is called as the crosstalk. So from the conductor A to conductor B, there is some coupling happening and the voltage is getting induced in form of noise, and it is causing the signal distortion in conductor B. So this is the basic. Okay, this is why we should look for the signal integrity problem in our layout. And as a signal integrity engineer, you should be able to define the identify these areas where this type of problem can come, and you have to provide the solution to the layout engineer, like how you can solve these issues. Okay, so this is a job of a signal integrity engineer. Now in digital now in digital electronics, so the signal is in form of 0 and 1. Okay, oh, and then will the increase in signal speed and decrease in signal of PCB and packages make handling signal integrity issue more challenging and complex. So right now I told, so the both the traces are going nearby each other. So as my signal, so as the size of the PCB reduces, okay, so in newer technology the PCB size is getting more and more reduced because of the demand or the component or other market requirements. So because of that, the density, the HDI, the high density interconnects are getting more and more dense. So that means more and more traces or more wires are going nearby each other. So because of that, this type of issue is more common. And also since the signal speed is increasing, so the transition from 0 to 1, 1 to 0 is also getting very fast. Now I've given example of 50 megahertz, but right now many signals are there board which are going up to 2 gbps, 3 gbps, 4 gbps, and 5 gbps. Okay, so there this type of issues are more prone. So in signal integrity, the basic what we do, we study the layout, we find out what are the possibilities and what are the areas where we can find this type of signal integrity problem, and then we use the tool to analyze those, to simulate those, and then we'll derive at the solution based on our concepts and learning. Okay, going to the next slide. What are the 4 T's of signal integrity? So the 4 T's of signal integrity, the very first T is called as the technology. So the technology speaks about what are the hardware design and what are the components which you are using, on what data rates they are working. Okay, what is the technology, like what is the edge rate? Edge rate is nothing but the 0 to 1, 1 to 0 transition. Higher the edge rate means it takes lesser time for it to transit from 0 to 1 and 1 to 0 logic. Then we come around the drive strength. Drive strength of the IC is in form of milliampere, like 2 milliampere, 4 milliampere, 8 milliampere. It tells you how much current it requires to charge the capacitor. That we will see in our further slides. We will understand it in more depth. Then we have a driver bandwidth which talks about the frequency bandwidth. Okay, let's for example DDR1, DDR2, they all works on different frequency. Let's say 100 megahertz, 200 megahertz, 400 megahertz, like that. So it tells about basically the functioning of the hardware. Okay, then after that it comes for the topology. The second T is called as topology. Topology speaks about the routing. Okay, so for now, what do you mean by routing? So routing is nothing but connecting point A and point B in electrical in a PCB through the copper. Okay, so all the copper interconnects everything in a PCB is called as the routing. So in routing process, you connect all the points in a to make the electrical connection. So in case of routing, you have multiple type of routing. So first, the basic type of routing is between point A and point B is called as point to point routing. Then we have daisy chain routing or flyby topology routing, which we use in DDR. And then we have T topology routing, in which it is a form of T. So one wire goes and then it divides into two. Then again those goes and divide into two. So it's form a T topology. And then we have star topology also. In the center the driver will be sitting, and all the fan outs will be across it going to the receiver. So that is called as a in form of a star. So that is called a star topology. And then the third T is the T line parameter. T line stands for transmission line. So as I told, routing the connection between point A and point B, we call it, is a layout engineer call it as a trace, but as a signal integrity engineer, we call it as a transmission line. Okay, we will learn that about transmission line in the next slide. Okay, so for the time, just remember the T line parameters. The first parameter is called as impedance, which is the AC resistance offered by the transmission line to the signal. Then we have propagation delay, which tells about the time taken by the signal to travel from point A to point B. And then we have the coupling, which we will see in our further slides. And then at the last we have termination. So termination is a methodology which we use to terminate the signal at the end point, so that we don't see reflections. Okay, so for right now, just remember the termination is a type of method which we follow to terminate the signal, so that we don't see any reflection arising from the end. So once the signal goes from driver to receiver, if the receiver is not terminated properly, the signal will reflect back to the driver. Okay, it will bounce back to the driver, and it will create some ringing over there in the driver side. So to avoid that ringing or this overshoots and undershoots, we provide termination over there. So termination absorbs the signal completely, so that there should be no bounce back of the signal. That we'll see in the future slides. Okay, what is termination? So now what is transmission line and signal propagation delay? So the very basic definition of transmission line, it is the electrical interconnect which is used to distribute energy. So distribute energy is nothing but to carry electrical energy or the data from one point in a circuit to another point in a circuit. Okay, this is a basic definition of a transmission line. So there are multiple types of transmission line depending upon the type of data. For example, the power lines, then we have cables, then we have copper traces in the PCB, then we have optics also which carry the optical information, so optic cables, then we have antennas and all to carry the RF signals, radio frequency signals. So these are all form of transmission line which carry energy from one place to another, which helps to distribute the energy. Okay, so what is the purpose of transmission line? So its purpose is to establish the communication between point A and point B. It can be analog, it can be digital, it can be optics, or it can be RF. Okay, radio frequency, that is the wireless. So now what is the, so now you can see on the top right corner there is one photo attached. So there we are seeing one is the transmitter and the second is the receiver. Okay, so from transmitter is a point A and receiver is point B. We have a signal path which takes the data from point A to point B. Okay, which takes the electrical energy from point A to point B. Now you can also see at the bottom we have a current return path. So all we know is like for a circuit to get completed, for the current to flow, we required a complete path. Until and unless the path is not completed, the current will not flow. Okay. So we, for the return current, we call it as a return current path, which is another conductor. Okay. So with this we complete our circuit, and the signal flows from conductor A to B through signal path and return back from B to A through the return path. Okay. So that is why it is said the characteristics of a transmission line, it consists of at least two conductor. So first conductor is to take the energy from point A to point B. Second is to bring back from point B to point A so that the circuit gets completed. Then we have then the second property of transmission line, it should be having a uniform cross sectional area. Okay, the cross sectional area means the width of the transmission line or the thickness of the transmission line should be same throughout the channel. Okay, it should not change. Why it should not change, that we will read in our study in our future further slides. Okay, then we should have a uniform impedance of a transmission line. So the transmission line should have a uniform impedance throughout the channel. And also you should have losses, means the transmission line should offer very low losses to the signal. Otherwise your signal will get more and more distorted and ultimately it will lose its property or integrity. Now what is the definition of instantaneous impedance versus the characteristics impedance? Instantaneous impedance of the transmission line is the impedance at that position where Vt and It are changing. Okay, so instant point of time when the signal is flowing into the transmission line, it is seeing some impedance over there, and due to that, that impedance is called as the instantaneous impedance, means the impedance at that instant of point what the signal is seeing. Okay, and the characteristics impedance of a transmission line is the one value of instantaneous impedance in a uniform transmission line. So once your transmission line is uniform, then whatever the value of instantaneous impedance throughout the transmission line becomes your characteristics impedance. So in general we have 50 ohm, 35 ohm, 75. These are the standard values of characteristics impedance which we generally use in our transmission line to design the transmission line. Okay, now next, what is impedance of a transmission line and how it depends? Okay, so just now we see what is characteristics impedance. So now on what factor those impedance depends upon? So the very two factor on which the impedance depends is the capacitance. that is denoted by C, and the inductance denoted by L. Okay. So the capacitance and inductance of the trace determines what will be the impedance of the trace. Okay. So higher the capacitance of the trace, lower will be my impedance, and higher the inductance of the trace, higher will be my impedance. So impedance of a trace is directly proportional to the inductance and inversely proportional to the capacitance. The formula of the characteristic impedance Z naught is given by root over L by C. Okay. L, and then a small l denotes the per unit length. So inductance per unit length and capacitance per unit length. Okay. Now, what is propagation delay? So propagation delay is the time taken by the signal to travel from point A to a point B in the transmission line. So it is nothing but the time taken by the signal to travel from one point to another point in the circuit through the transmission line. So how much time the signal takes, that becomes the propagation delay of the transmission line. So longer the path, the longer the transmission line, more time it will take. So higher will be the propagation delay. Okay. So propagation delay also depends upon inductance, capacitance, and the transmission line length of the transmission line. So it is directly proportional to the inductance. Now, how it is directly proportional to the inductance? As we know, the current is flowing into the conductor. It induces a magnetic field, okay, magnetic flux. So as per Lenge's law, that magnetic flux opposes the flow of current. So current sees more opposition in flowing. So it slows down the flow of current, which results in more propagation delay. Okay. Similarly, as per capacitance, so higher the capacitance, more time the signal will take to charge it up. Until and unless the capacitance of the trace is not getting charged up, okay, capacitance per unit length is not charging up, the signal will not move further. So it has to move further, it has to charge all the capacitance throughout the way in order to go further. So higher the capacitance, more the time it will take to charge it up, and then the delay will increase. Okay. So from where the capacitance is coming, that should be the question. So if you see a PCB layer, okay, a PCB board, we have few copper board, then we have insulator between them to insulate two copper layers. Okay. We have multiple copper layers and dielectric layers sandwiched with each other. So like copper dielectric, like that we make like 6 layer, 8 layer, 10 layer, 20 layer, how based on our design requirements. So between the two copper we have a dielectric. Okay. So that is nothing but acting as a capacitor. So in a capacitor also, the minimum requirement to form a capacitor, you require two metal plates, which are the two copper plates over here, and a dielectric insulation, which is nothing but the dielectric material of the PCB. So different types of dielectric material comes based on our design requirement. We choose it in order to maintain a proper impedance, as well as to keep the low losses. That we will learn in the course of signal integrity, like how to choose the prepug, how to design the stack up. Okay. Then in the next, now what is reflection in transmission line? So reflection is a problem which is very prone and very common in all the high density interconnect boards, and it is also present in low density boards also, because it is something related to the termination. Okay. So if the signal at the end point, at the receiver point is, or the source point is not terminated properly, it will result in the reflection. So what is reflection? So when a signal travel down the transmission line through all the interconnect, and if it sees any impedance mismatch, okay, any impedance mismatch due to impedance discontinuity in signal and return path, then a part of signal reflect back to the source. So let's understand this definition. So suppose there is one point A and point B. We have a transmission line of 50 ohm impedance. Okay. So a 50 ohm impedance, in one case, uniform impedance of 50 ohm. So this case, when transmission line, okay, so signal point A to point B, and no impedance discontinuity. Impedance discontinuity means by any mean the impedance of the transmission line is getting changed. So how a impedance of a transmission line get changed? If the conductor is thick, it offers the impedance drop. Or if the conductor is becoming thin, that at that point the impedance may rise. So if the trace is crossing through a via stands for vertical interconnect access. Okay, it helps us to connect one layer to another layer of the PCB. So the via shape mat also changes, because for that the impedance also changes, because the via structure and shape will not be similar to as a trace. Okay, so at that point of time you should ensure like the via, whatever the via you are designing, it should match the impedance of the trace. And when it is passing through some component, and in second, or it is passing through any cutout in the reference plane, so in the return part if there is any cutout which is calling, like here it is mentioned, the return path, the discontinuity in the signal and the return path. Okay, so these are the few impedance discontinuity uh, where the impedance can get change. And due to that impedance change, the signal reflects back. Okay, so for example, let's say the signal is the formula, if I use V equals to IR. So if my R is constant throughout the trace, my voltage will be constant. But due to some reason, because my trace suppose gets thinner, okay, if it is crossing into the breakout region or going somewhere where the if you cannot maintain the proper trace width, so at that point of time my impedance is going to increase. So if my impedance increases, V equals to IR, if we use, my R is increasing and the voltage will also increase over there. So now suppose we were sending a 3.3 volt signal. Now because since my R is increasing, okay, because my trace is going thinner, so my impedance will also increase, and then we will see a rise in the voltage. So now 3.3 volt signal will not be 3.3 volt, it can shoot up to 4.5. If you see the bottom rightmost picture, the signal settling time, if you see at the end, it is showing around 3.3 volt. But since my head signal head saw a higher impedance over there, so my signal shooted up to 4.5 volts. Okay, and then again it came back to 2.5 volt, again 3.8 volt. So this is called as the ringing. Okay, so this is what the ringing is, and it is present because of the impedance discontinuity. So as a signal integrity engineer, your job is to identify these places where my ringing is present, and to provide the proper termination, how to terminate the signal. You should provide the guideline to the design engineer, like how you should terminate the signal, so that there should be minimum ringing. Okay, the ringing cannot be completely removed. Okay, it will be present, but it should be within the threshold limit. So the threshold limit, generally what we use is 10% of the VCC voltage. So in this case 3.3 volt is my VCC. So 3.3 volt, 10% of that comes around 300 millivolts. So maximum up to 3.6 volt we can acceptable. It is acceptable, but not more than 3.6 volt. So if it is going more than 3.6 volt, then you have to rethink of designing everything, designing the trace, or to give a proper termination. You have to design the via properly, so that you don't see any high overshoot over there or high ringing over there. So, as I told, what are the types of impedance discontinuity? The first is the change in trace geometry. Second is the stubs, connected layer change through via, change in reference plane, or the breakout in or the discontinuity or the breaking in reference plane, a branch or a T, or any discrete devices, what other RLC transformer, anything, because the pin resistance pin will offer a different resistance or impedance of what the trace is offering. So, so for that we have mentioned the discrete devices, because of the pads thickness and all, the impedance discontinuity occurs over there. So now we will understand reflection into more depth. Okay, so what is reflection coefficient and how it impacts the reflected signal? So the reflection coefficient describes the fraction of the voltage that reflect back to the source. It is given by the formula V reflected by V incident equals to Z2 minus Z1 by Z2 plus Z1. It is denoted by a small sub p, which is the reflection coefficient, or you can call rho. So now what is Z2? So Z2 and Z1 depends upon the direction of your signal flow. Okay. So in the picture, if you see, we have an incident signal, okay, entering the board from the thicker trace, which is 50 ohm, and then you see after some time the trace is getting thinner, which is resulting into 75 ohm of transmission line impedance. So we that is what the point of impedance discontinuity. So that point by impedance is getting changed. So because of this, what will happen? My reflection coefficient will be a positive number. That means, so Z2 is 75 minus Z1. So 75 minus 50, 25. And then we have 75 plus 50, 125. So if we divide both the value, we will get around zero point 0.4 or zero point 0.5 as a reflection coefficient. Okay. So now my voltage getting induced into the section B. Section B is the Z2, where the Z2 is 75. Section A is where Z1 is equals to 50. So the voltage induced into section B will be given by V incident, that is suppose 3.3 volt of signal is coming, multiplied by the reflection coefficient. So in this case our reflection coefficient is a positive value. So that amount of voltage will get added up to the incident signal, and we will be seeing the overshoot of that value over at region B. Okay, this is how we calculate what should be the resistance. And to also to get an accurate value, we derive a bounce diagram. Okay, right now I have not included a bounce diagram because it will be high level for you all to understand right now. So in that, a lot of mathematics is involved to derive a bounce diagram. So the basic five cases I have taken from that bounce diagram only. So the case one is where Z2 is greater by than Z1. It is the same case which I explained just now. So in that case, the reflection coefficient is a positive value, and we will get a positive voltage reflected back. Okay. So a positive voltage value of voltage will get reflected back, and it will be get added to the incident signal. And if in case suppose the Z2 is less than Z1, so in case so we will reverse it. So for example, the Z2 trace is more thicker as compared to the Z1 trace. So in that case, the Z2 will be less than Z1, and we have a negative voltage reflected back. And okay, and we will get a negative. So instead of 3.3 volt, 3.3 volt will get bring down to whatever the negative voltage which is reflecting back from the source, from the receiver. And then in case if Z2 is equals to Z1, then the reflection coefficient becomes 0. Okay. And in that case, we don't have any reflection observed because the reflection coefficient is 0, and you multiply incident into the reflected, we will get 0. Okay. So the reflected voltage equals to incident voltage multiplied by the reflection coefficient. Reflected voltage will come 0 because my reflection coefficient is 0. Then we have another two cases which is not very common, but we will understand it. So case one is when the end of the transmission line is left open. Open means it is there is no connection. Okay. Or there is a very very high value of impedance termination is used, for example 1 mega ohm or so on. So in that case, my 100% of the signal will get reflected back. Okay. My 100% of the signal will get reflected back. So if you are transmitting 3.3 volt signal, you will be seeing around 6.6 volt signal at the driver, because 100% of the voltage is getting reflected back. And if there is a short at the end of the transmission line, so shorting means if there is some short at the end of the transmission line, then we have 100% negative voltage reflection. Means if the transmission voltage is 3.3 volt, 100% of the negative means minus 3.3 volt, and both add ups to get a 0 volt. That is why for a short circuit you get a 0 volt into the voltmeter because of this. So 100% negative reflection happens. Okay. So these are the five cases which is generally the first is what we generally care for, and four and five is not that much common because no one leaves the transmission line open or shorted. Okay, so yeah, now going to So this is the bounce diagram. Okay, so I have added a very basic of how to derive a bounce diagram. So we will understand it a very basic terminology. The first is the voltage source. Okay, so as we know, in an ideal voltage source will have a very, so it is ideal voltage source is the one which has a zero source impedance. Okay, with zero source resistance. So but in our real case there is no ideal voltage source. So voltage source also have some output resistance, okay, which is given by the R source. So a source voltage is of 3.3 volt. We have 3.7 assumed as the R source resistance, and then we have a transmission line T1, Z naught equals to 50 and TD is equals to 100 picosecond, and then we have R termination resistance use of 1000 ohm, that is 1 kilo ohm. Okay, so this simulation is done into LT Spice, which is the open software. You can also go and try this. So for that reason, I have used the LT Spice. And now voltage launch. So there are two parts now. Okay, the first is the voltage launch into a transmission line. So in ideal case, when the source resistance is zero, whatever the voltage the source V source you are seeing 3.3 volt, the same voltage will get induced into the transmission line. But now since you are having a source resistance of 3.7 ohm, you will not see a 3.3 volt signal. So what voltage you will see over there is given by the voltage divider formula. V launch equals to V in cross multiplied by Z naught by R source plus Z naught. Okay, V is nothing but 3.3 volt. R Z naught is the transmission line impedance 50 ohm, then 50 plus 3.7. So it is nothing but it is forming a parallel voltage divider network, and we will get around 3 volt signal into launched into the transmission line. So mean to say around 10% of the signal, that is 300 millivolt of signal, will get dropped within the source itself. Okay, and 3 volt of the signal will get launched into the transmission line. And then we'll see that then after that here is a reflection coefficient formula. So in our case z2 becomes the, so now the reflection coefficient, as I told, it depends upon the direction. So from when the signal is traveling from source to the receiver, okay, means from the voltage source to the receiver, so the reflection coefficient of at the receiver, we are calculating the reflection coefficient of receiver. So z2 minus z1 by z2 plus z1. So z2 is nothing but this one, okay, because the signal is traveling from this, the head of the signal is seeing this as the path. So this region becomes my z2, this region becomes my z1, because signal is traveling from here to this direction. So rt minus 50 by rt plus 50 will give you the reflection coefficient at the receiver. Okay, and same way if the signal is bouncing back, okay, so bouncing back signal will also sees this as the transmission line, and it will again the same reflection coefficient formula will be applicable on that. So now since the signal direction is from B to A, this region of the, it becomes the Z2 and this becomes the Z1. Okay, so Z2 is nothing but the R source, okay, this one, and Z1 is nothing but the transmission line impedance. Okay, this is how you calculate the reflection coefficient. So right now it will be more from just seeing it is complex. It will be easy when you take a pen and paper, and we will, when we will calculate this, that time it will be more easy for you to understand. Okay, so right now just giving an overview of how we calculate how much the reflection will occur. Although the tool can also do this, but you should know the background on what the tool is working and how the tool is calculating. Okay, so you should know the background of the calculation. The mathematical calculation is very important to understand in order to predict the range in which you will get the overshoot or undershoot or the ringing. So the next is the what is differential signal, what is advantages and challenges of a differential signal. So a differential signal is basically two driving pins with opposite signal edges. Okay, so two traces are going side by side to each other in with complementary signal of the other one. Okay, in suppose in one trace if logic 0 is going, in other trace logic 1 will be going. So it is complementary of each other. So and the signal which is intercepted at the end, the receiver takes the difference of both the voltages, like that is V differential equals to V1 minus V2. Okay, so what are the advantages of a differential signal, why we are using this? So this gives you the noise immunity. Okay, how it gives a noise immunity? The first one is the voltage. Suppose 0 to 1 will have a magnetic flux, and 1 to 0 will have a magnetic flux in the reverse direction. Okay, so both the magnetic flux in the forward direction and the reverse direction gets coupled with each other, because since the both the traces are in very close proximity to each other, and it cancels out. Okay, so whatever the noise which you are seeing over there will get eliminated. Okay, because both the magnetic flux are canceling out each other. And if suppose some from somewhere the noise get induced, okay, since both the traces are very near to each other, okay, so the same amount, almost same amount of noise will get induced on both the traces. And since my differential receiver takes the difference of both the signal, hence it will not consider that noise. Ultimately it will take as the difference remains the same. Okay, the difference remains the same, and whatever the value, whatever the logic it want to interpret will not get distorted. Okay, because it is taking the difference of the signal. And since the noise is present on both the signal, it becomes a common mode noise, and it differential pair eliminates the common mode noise. Okay, it don't take account into the it don't take the account for the common mode noises. That is the benefit of the differential signaling. So it provides better noise immunity as compared to single ended topology. Then second, it emits low EMI noise compared to single-ended traces. So low EMI noises means low electromagnetic interference, because both the magnetic couplings are getting cancelled by each other. Okay, so ultimately there is no emission of the EMI. It eliminates the power plane noise, since the return path is another trace and not the reference plane. Now, here since I have not explained you the return path, it is difficult for you to imagine. So the return path here in this case will be the another conductor. Okay, the conductor which is nearby. So one part of the conductor is taking that signal, and the other part will become as the return path. So in this case, the bottom copper, you can see here there is one copper plate over there. This does not becomes the return path. Some amount of signal will flow, but not in like not like what it flows in case of a single ended signal. Okay, so these two signal becomes the return path and the signal path of each other. And it provides the high data rate. Okay, since we get a noise immunity, we can transfer a higher data rate over this signal. It will not get distorted. Now in this differential signal, we have two modes of operation. One is even mode of operation, one is odd mode. So even mode of operation is when the signal is flowing in the same direction in a differential pair. Okay, and the odd mode is when the signals are flowing in opposite direction. So in one pair, generally the differential pair is used in case of odd mode only. That is a very mode. Even mode comes into picture when we have a common mode noise, because the noise is getting induced is same, so its direction will be also same. So that is what we consider the even mode, but it is case when we have noises. And in the normal scenario, we classify it as odd mode, because the signals flowing is opposite direction, that is driven. So in this 0 to 1, and here 1 to 0. So this is the normal mode, odd mode operation of the differential pair. Okay, and then what is crosstalk, and what is near and crosstalk, and what is far and crosstalk? So yeah, what is the challenges of the routing a differential pair? Okay, so the challenges for routing a differential pair is, the first is the you require more spacing. Okay, as compared to single-ended signal, since you are having two traces pair which has to go side by side throughout the throughout the path. So where the coupling, you cannot break the coupling in the sense you cannot change the distance between both the conductor. If your distance between both the conductor is changing, then you will lose your impedance, because impedance of the differential pair depends upon the distance between the two conductors. Okay, the second is you will lose the noise immunity. Now whatever the EMI coupling which you were having, the magnetic coupling, that will get break and will start emitting the EMI noises. Then the common mode noises will also increase, because now no more the two conductor are into close proximity, they are far from each other. So whatever the noise which is getting induced on conductor A and B will not be same. Whichever conductor is near to the noise source will have a more noise induced into it. So because of that, these are the few challenges which we face while routing a differential pair. Then in case of single-ended traces, you use a single-ended via, but in case of a differential, it is differential, give the clearance according to the differential impedance. You have to run a lot of iterations and to check which VI stack is giving you a proper impedance. Okay, you should match the differential trace impedance. So in normal scenario, 100 ohm, 120 ohm are the common differential impedance uses 90 ohm. So like these are the uh, uh, basic these are the very common impedance value which we use in our day-to-day like PCB designing. Then the second most common, which I explained in the first slide, that is a crosstalk. Okay, so what is crosstalk and what is near end crosstalk and what is far end crosstalk? So crosstalk is something the electrical disturbances caused in one net because of signal transiting in nearby net is called the crosstalk. So as you can see in the photograph, the red ones are the magnetic fields, okay, which is around the conductors, and the blue ones are the electric field, which is across the conductor, okay. So electric and magnetic field lines are orthogonal to each other to any point. As we know, they are both makes a 90 degree, they are orthogonal to each other. So because of this, since the electric and magnetic field, it gets coupled to each other. If you see the both the conductor in this case are very close to each other, okay. Although here we are not seeing any red lines crossing each other, but if we bring both the conductor more close to each other, then we have a magnetic coupling. Because of that magnetic coupling, I explained a voltage get induced into the conductor B, although there is no a direct electrical connection, okay. So since the voltage get induced into conductor B, it will have some noise getting induced, and because of that noise my signal in conductor B will get distorted. So what is the reason for crosstalk? Changing electric field and magnetic field around a conductor that reaches another conductor, okay. That reaches another conductor means getting coupled to another conductor. Electric field lines go between the conductor with different potentials. Magnetic field line go around a conductor that has current flowing through it. So magnetic field line is always across the conductor, and electric field lines are always magnetic fields are always around the conductor, and electric field line is always across the conductor between the two conductor, negative and positive. It forms the field lines. Okay. So now next. So now what is next and fixed? So next stands for the near end crosstalk and fixed stands for far end crosstalk. Okay. So what is near end? What is far end crosstalk? So this is the simulation result which I have taken from the hyperlinks tool. So hyperlinks tool, in hyperlinks you can do this crosstalk analysis. So this is the driver. Okay. U1.1 means the pin number. U1 is the ref desk of the driver. Then we have a TL2, that is a transmission line. Then we have a R1 resistor, and we have a second one. I have made it as a shorted to ground. Okay, so this is a dead transmission line. Means why I have kept it dead? So that I can study whatever the voltage is getting induced into this line, only that voltage value I should be able to study. So whatever, if I make this transmission line as live by giving the driver and receiver, I will be it will be difficult for me to understand the graph, because this will also have a voltage induced into it, okay, because of the driver. This will have a signal into it, and that signal will also that signal will get add up with the noise, and the graph will change. So it will be difficult for me to understand how sorry, how much noise is getting induced from this transmission line to this one. Okay, so for that reason I have made this transmission line as dead or shorted it to ground. So the potential across this transmission line is zero. Okay, there is no voltage on this transmission line. So now as this pointer, you can say this yellow arrows, red arrows are, you can see on the graph also. Okay, so wherever the red is there, so this is the signal over there. So now here we can understand two things. We will understand here the propagation delay also, we can understand. So now since this both transmission lines are same, okay, a 50 ohm 50 ohm termination I have to give, because in tool you cannot short the transmission line to 0 ohm. Okay, tool don't allow you, because we generally don't do it, as I explained. So tool also don't allow you, so you have to put a same termination, same impedance value register over here, and you have to short it to ground on both the corners. Similarly here also I have to short it ground by using 50 ohm. So since this is 50, this is 50, you will not get any reflection. So just see the yellow signal and the red signal. Yellow signal is at the driver. See the signal is very clean up to 500 millivolt, and it is going up to 500 millivolt. Since my termination is of 50 and this is 50, I am not getting any impedance discontinuity. My signal is very smooth, and I am not having any overshoot and undershoot or any ringing. Then if you see the red signal, it is not starting from here, but it is starting from here. Why this much distance? Because this is the propagation delay of the transmission line. What is the propagation delay? See, 731 picosecond is what it is given here. 5 inch means it is the 5 inch of transmission line. Couple stack up means I have coupled these two transmission line. So hyperlinks will not understand if you place two transmission line. It don't calculate the distance between it until and unless you don't couple. There is one option in the tool, which in the line sim, where you can couple the two transmission line. So the tool understand, okay, these two transmission line are very near to each other, and you can define the and you can define the distance also. So now if you see the red signal, it is starting around 800. Why? Because there is 731 picosecond of delay. So 731 picosecond, if you see 200, 200, 200, 600, and then we have over here 100. 600 plus 100, 700. So 700 picosecond of delay is happening from the signal origin, that is yellow signal, and the red signal. So 731 picosecond of delay is happening. Okay, this is how you can the tool tells you the delay of the transmission line. Then we have this point. These are the 2 points. Okay, one is the purple point and one is the green point. So purple point is nothing but the near end. So purple signal tells you the near end crosstalk. Near end means, because why we are calling it near end, because it is near to the driver side. Always remember the direction matters a lot over here. So driver side, this is near to the driver side. Okay, this is towards the driver side. That is why we call it as near end crosstalk. Whatever the coupling is happening over here will be termed as near end crosstalk. And this point, green point, is the far end crosstalk, which is far from the driver side. Okay, always the driver side is taken into account, not the receiver. Okay, so the driver side, this is the far from the driver side, because this transmission line is there. Now it is looking nearby, but once you go on the board, so this is one point of the circuit, this is somewhere another point of the circuit. So this is what the distance between that. Okay, and this is a far end, this is a near end. So there, now if you see this near end crosstalk, there is a positive value which is going through. Once it rises and it going throughout the trace, it is constant, and then it is going and it is dying over here. Okay, but as compared to far and crosstalk, you are not seeing until the signal head reaches over here. Once the signal head reaches over here, then we have a very high peak, and then suddenly the peak is getting died. Okay, so this is a behavior of near end and far end crosstalk. Also this polarity also matter. Near end is having a positive and the far end is having a negative. So this, you have to study the behavior of near end and far end crosstalk. Why? What causes the near end crosstalk? The capacitive coupling. The causes the far end is the magnetic coupling. So all that direction also matter, the polarity also matter based on the coupling. This you have to study in depth. Okay, in the signal integrity course, I have covered this into depth, where you can without this you can calculate what will be my polarity and how much overshoot, like how much amplitude of crosstalk I will be seeing over there. Okay, so now in the next, we go into the losses in the PCB. So what are the types of losses in PCB? The very two classification of losses in a PCB. First one is the dielectric loss. Second is the conductor loss. Okay. So dielectric loss is what happens at a very, very high frequency. Okay. So at a very high frequency, when the signal is flowing in the copper, and in the middle we have the dielectric, and then we have the another copper. So the return path is going through the dielectric through the magnetic and capacitive coupling into the return path. Okay. I have not explained the return path. That is why it is difficult to understand now. So the magnetic coupling happens between the signal part and the return path. So now the dipoles in the dielectric rotate as they are pulled by the electric field. Okay. So because the electric field get induced into the dielectric because of the two copper plate, so since the electric field is very much changing because it is a high frequency signal, 400 megahertz. So because of that electric field, it vibrates the dipole. Okay, it vibrates the material PCB, that dielectric material, it vibrates, and because of that vibration you get losses in form of heat. So that is the dielectric losses. Okay, the PCB, the material gets heats up because of that high vibration into it because of the changing electric field. So faster the changing electric field rotates the dipole faster. Faster the dipole rotates, more is the amount of heat dissipation. Moving dipole dissipates heat. High frequency electric field losses more energy in the decay. Decay stands for dielectric constant. Okay, decay. Then we have what called as conductor losses. Okay, so the basic of conductor loss is the voltage drop, because we know a conductor will have some resistance across it, and across when once the resistance is there, we have some voltage drop across it. Okay, so voltage drop is one of those losses in the classification for the conductor loss. Then we have copper foil losses. Construction is not smooth. So if the copper foil, the copper layer, if you see, okay, there is multiple types of copper layer. Okay, what we call it as finishing. So the finishing of the copper layer also matter. So generally, what we choose a value between smooth and rough. We cannot make it so smooth, otherwise the dielectric, which is on the top laminate, will not get properly sit on the copper layer. Okay, we will have some mechanical weakness issue will come over there if the copper foil is too smooth, and if we make the copper foil too rough, in that case we get the conductor losses. How? Now there is, now suppose at the low frequency, they see the graph in the second picture over here. In case of a low frequency, the red one is my electron density. Okay, so this is my conductor. Okay, and the current is uniformly distributed across it. Okay, this is my return path, the solid one, and this is my signal conductor. Then we have a frequency goes higher to 10 kilohertz. Now you see the placement of the electron is only between this region. Okay, okay, only it comes to this region. Then we goes to the 1 megahertz. Now you see it is coming to the surfaces. Now it is no more inside, now it is coming to the surface. So this whole phenomena is called as the skin effect. Okay, so skin effect, this whole what is happening over here is called as a skin effect. Now we further increase the frequency to 100 megahertz. See, it is now the electrons are completely on the surface. Okay, there is no electron in the inner of the material or the copper. All the electrons are on the surface. Now the electrons are flowing on the surface, and if your surface is rough, the electron sees a lot of distortion in flowing. Okay, it cannot flow smoothly because your surface is very rough, and it's offer a high impedance or a high, changing it's offered a high noises to the flow of electron. Okay, it cannot flow as it was flowing in case of a smoother surface. So dispersion edges and roughness effect comes above, like say 100 megahertz and all. This things comes into picture. This whole phenomena is called as the skin effect. So the roughness profile and the depth vary by manufacturing. When skin depth approaches the roughness depth, the loss increases usually around 10 gigahertz. Okay, this is very more prone in a very, very high frequency around 10 gigahertz, where the skin depth Skin depth is nothing but the depth where the electron is flowing from the surface to the inner surface. So this red picture you can see, that is your depth. Whatever the thickness of the red color region is there, that is your skin depth. So there where the electrons is flowing. So when the skin depth approaches the roughness depth, so if the roughness depth is, let's say for example, 1 mil, and your skin depth is 1 mil, so now all the electron which is flowing through this rough surface, and because of that roughness, the it opposes the flow of electron, and you see a high conductor losses. Also, the distance covered by the electron also increases, because in case of a rough surface, it flows from here to here very smoothly. But once the signal becomes, the surface become rough, now it has to travel a longer distance. It has to go down, up, down, up, down. The distance increases. Okay, because of that, also the signals get more distorted, because that distance is increasing. There are different models for surface roughness resistance. Okay. Then this is a attenuation and insertion loss. So attenuation in a PCB refers to the gradual loss of signal strength as it travels through the PCB traces. Attenuation is when your signal gets weaker and it moves across the board. So attenuation is given by the formula P in by P out. P in is the power, input power by output power. So this is case of an idle signal which is traveling, okay. And then this is the case of the receiver. So this is a transmitter. We are giving a idle signal of 3.3 volt, okay, without any distortion. But as it is flowing through the transmission line, see that signal strength is getting weaker and weaker. So this is what the dampening of signal is happening, and it is getting more weaker because of the transmission line distortion or attenuation, you can say. Okay. So now at the end, so we will see what is hyperlinks. Okay, so hyperlinks is a comprehensive suite of tools for analyzing and verifying high-speed printed circuit board PCB designs, encompasses signal integrity and power integrity. So there are two types of analysis which we do on a PCB. One is multiple type signal integrity, power integrity, EMI, EMC, uh, uh, and based thermal. So these are the four type of analysis which we do. But in this course, we will cover only the signal integrity concept, and a little bit of power integrity also we will cover, because it is essential for us to learn the power integrity as well, in order to produce a good signal integrity solution. Okay. So in hyperlinks, it uses both pre-layout and post-layout. Pre-layout is the one before the layout is done. Okay. Once the design requirement comes, then you will run a pre-layout simulation in which you will tell how to design a via, how to give the termination, how to do the patch stack designing, everything, how to do the placement of the component, the discrete component, everything you will tell, everything you do in the tool. So for that, we have a tool called as line sim. Line sim is used for the pre-layout, which I showed just the example, that was a line sim, where you can study the behavior of the electrical circuit. Okay, so it has the power where you can do the crosstalk analysis, DDR analysis, and many types of compliance, which I will explain in the next slide. We can do perform over there in line sim itself, and based on that you can derive the constant for the layout engineer. And using that constants means what is the trace width, what is the pad thickness, everything in form of layout, you will derive the constant. You will prepare a report and you will share it to the layout engineer. Layout engineer will take that report as an input and will design the layout according to the signal integrity, by keeping the signal integrity constant in mind. So this reduces the overall project execution time, because once the layout is done, then it is very difficult for a signal integrity engineer to provide solution, because uh, because the layout is already done, and you have no room, or you don't have the flexibility to change much. Okay, so whatever you can do, you do. So that is why it is very much recommended to do a pre-layout before going to a layout design. Okay, and once your layout is done, then you can use this tool called as board sim. You can import the whole PCB board over here, and you can perform the simulation over here. So this board sim gives you a more accurate data, on what more accurate data regarding the simulation, because it is performing it on an actual real PCB board, which is going which in future will go for the fabrication. Okay, so the board sim analysis give you a very very accurate data as compared to a line sim. Line sim is what you create, but the board sim is what it does on already a layout is created. So this is more accurate, it gives some more precise data, okay, which you required. And then we have multiple like oscilloscope, we have ez wave we generally don't use, but oscilloscope is what I showed you, where the plots and all will come. So this is a overall of hyperlinks. Okay, so there are, yes, there are multiple vendors which offers this for like Keysight offers the ADS. Okay, Keysight offers the ADS, the Ansys offer the SI wave and HFSS, the Siemens offer the hyperlinks. Okay, and Cadence offers Sigrity Aurora. So why I have choose hyperlinks is because hyperlinks is a very what you can say engineer friendly tool for a person who is starting the signal integrity journey. Okay, so if you want to start a signal integrity journey, the hyperlinks is the one of the best tool in the market, which can give you the brief thing, okay, which can help you to understand better. The UI is designed in such a way that it can help you to understand better, uh, and you can explore more signal integrity concept more freely rather than getting stuck into the UI. Okay, so what we will be, this is the overview of the course, signal integrity course. Only is also start your career. Okay, if you want to start a career into electronic, uh, include PCI also. If you are able to, if you are able to understand this in one is the frequency domain in which you are heavy about the frequency of operation. Okay, for example, what I said in the earlier, like we have a frequency, let's say 100 megahertz, 200, 300 in gigahertz, 1 gigahertz, 2 gigahertz. So how your channel is behaving on the high frequency. Okay, what are the losses it is increase like, so you have to understand the frequency domain simulation also. I will be teaching you how to do the time domain as well as the frequency domain simulation to solve the singular integrity problem. Then we will able to understand the circuit application on how to read the data sheet. So data sheet is what to how to read the data sheet is what all the electronics engineer, whether you are from whatever background, you should know. Okay, you should able to read the data sheet. So data sheet is generally 100 200 pages. You don't read all the pages, but you should know how to, where to find the information in the data sheet what you required for the analysis. Okay, for analysis what you require frequency, you require the voltage logic level, you require the maximum operating voltage, recommended operating voltage range, insertion loss, return loss. All these are the parameter which you extract from a data sheet. So I will be teaching, so you will be able to understand the circuit application, and also how the circuit application is also given in the data sheet, like a basic, like how you can use place this component, what are the other types of component which you require to use this component, that is what it shows into a circuit application. So you should be able to understand the circuit application as well as able to read the data sheet. The student will get the quality exposure to electronic study work, industry work standards. So as I am from the electronics industry, I will be giving you the exposure about the work standard which we follow, what are the different types of work standards which we have to follow. Okay, and then we will be learning, they will be able to identify the signal integrity problem and able to solve it, providing the layout changes and recommendation. Okay, once you are done with all the course, at the end of the course, what I will be doing, I will be creating some of the issues into the layout. Okay, knowingly I will create those issue, and I will be sharing the layout file to you all, and I will be assigning the interfaces accordingly, and you have to tell me what are the issue present in that interface. Okay, how that interface is, what are the signal integrity problem present in that interface, and how we can solve those, and you have to solve it, and you have to tell me like, this is the recommendation which you will be giving me. Okay, so theory is what where I will be speaking a lot. Okay, and lab is where you will be speaking a lot. Okay, lab is what you have to do by your own. I will be there to guide you. I will be showing you first the demo, but at the end you should be able to perform the analysis by your own, because in the company when you go, no one is going to, there will be people to help and provide guidance to you, but at the end of the day you should be able to complete your job by your own. Okay, at the end of the course you will be able to work independently. That is my goal. Okay, this is my goal, to make you all work independently without any support, and we will be able to resolve the SI related problem on their own. So point number 9 is what the end outcome of this course. At the end of the course, they'll be able to provide independently with work independently without any support, and will be able to resolve SI related problem on your own. So I will make you that much sufficient. Okay, so that you should be able to work independently without, yes, you required guidance, but not completely throughout, because in the starting of the career phase you may require guidance, but at the end you will be able to work. Okay, you will be able to take 90% of the task, you should be able to complete by your own, asking us or without taking help from other. Okay, this was a brief of, with this we will complete the demo session, and if you have any doubt, please feel free to ask me now. Okay, you can unmute yourself, you can tell me, I will explain it again. It is over to you now.
Yeah, hi sir.
Yeah, tell me.
So it will be include the time domain and frequency domain. So the eye diagram will be also the part of these
Yes, eye
sections.
diagram. Yes, eye diagram comes into the time domain simulation. Okay, but in
Okay.
order to derive the eye diagram, you should know what is the channel characteristics. Okay, so to derive the channel characteristics, you will be using the frequency domain as well. So for an eye diagram to produce the eye, you should be able to time. First, you have to perform the frequency domain. Then, using that frequency domain data, you have to perform the time domain. Yeah, so I will be included into this course.
Okay. So the tool will be the only the hyperlinks, huh?
Yeah, tool I will have choose hyperlinks because it is more user friendly, right? If I use ANSYS and all, no, right now at this point of stage, you will not able to understand ANSYS. The UI is very complex, and it is the simulation, the solver which ANSYS use, it takes a lot of time. Okay, but it is also very accurate, but it consumes a lot of time, and because of all those reasons, I have choose hyperlinks to continue with this course.
Okay. So we will get the license, or we have to access the labs remotely.
That is that Uh, Shrikant can explain better right now. I guess you will be getting the lab access. Right, Shrikant? Yeah, your voice is not audible, Shrikant, if you are speaking.
And
Yes,
one more
surely,
thing.
no problem. You will get a lab access. Yeah, I guess RDP.
Okay, okay.
Okay. Yeah, RDP will be 24 by 7, right? In the brochure they have mentioned, right? So you will have the lab access for that RDP. RD lab access will be there.
Okay.
You were asking something?
I was asking CST tool that will also compatible with hyperlink so that if we get the chat version of CST so that we can it will help us.
Yeah,
CS.
CST Studio, right? For antenna and all which you use, correct? That one, right?
Mm-hmm.
Yeah,
Right,
so
right, huh?
yeah, that is for actually the CST is for the 3D, okay? So that is more into the 3D simulation. How much I have used CST, I have not much used CST, okay? Because in the industry level, we use generally analysis for 3D, okay? We use hyperlinks is also offers a 3D, but we rely more on analysis for the 3D, and I have used analysis. So CST, I'm not sure whether it will help you or not, but yeah, I cannot comment on the CST because I have not used much of CST. I have used it very little bit, but more for 3D we rely on ANSYS. Okay, yeah, ANSYS is the gold standard for what we use in industry for the 3D simulations. For the waveguide and antenna simulation, for that thing we use ANSYS more in the industry. What I can say.
Okay, okay, understood. Thank you.
Yeah, welcome. Okay, so we will be ending the, I guess Shrikant is not here, so we will be ending the demo session. Okay, so please feel uh, open to connect with the team. Okay, VLSI Guru, if you want any further assistant.
Sorry, just to interrupt you.
Yeah, yeah,
So
yeah.
you are from the basically from the signal integrity background
Yeah,
in
I'm a
your.
signal integrity engineer. Yeah.
Okay,
Earlier I
okay.
was working in Wipro. Now presently I'm working in a German-based company.
German-based company.
Yeah, German-based.
Okay, okay. Okay, okay, fine.
Okay, so I will be
Uh,
ending. You have any other question?
no, 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 no. It's okay. I'm done.
Okay, okay. So for any other query, right, reach out to VLSI Guru, okay, for that.
Yeah, yeah, sure, sure.
Okay,
Okay,
okay. Thank you. Bye.
okay. Thank you. Bye.